Cool, and we're back. So the physical audience is still getting inside, and when I started talking, people actually realized we're going to start with this session with Urs Peter and some early access Project Loom versus Kotlin Coroutines. I love a good versus. So have fun, everyone, and enjoy. Questions will be at the end. There'll be plenty of time for that. Go ahead, man.
Cool, excellent. Thank you. Welcome, everyone. Nice to see you from this place, which I haven't had for years. My name is Urs Peter. I call myself a senior software engineer, as you can see, based on my gray hair. I started out with Java, moved on to Scala, and for about 4 years I'm programming exclusively in Kotlin when it comes to backend logic. Besides that, I'm also a, dare to say, passionate trainer. I love to spread the word about Kotlin. And since the beginning of this year, I may call myself a certified JetBrains Kotlin trainer. Okay, it's very nice to meet you, and I would like to take the opportunity to get to know a bit more about your knowledge about this subject. So, first of all, who of you have worked, and with work I mean a bit kind of serious, not only playing around, worked with threads, low-level threads, wait, notify, latches, semaphores, and so on? Okay, not many. Check. Who have worked with reactive toolkits like Reactor, Webflux, RxJava? A little bit more as I can see, but also not still very many. And last, who has worked with coroutines? More or less about the same, about 1/3 I guess. Okay, so I think for the ones that are new to coroutines, let's start out with them because they give us the baseline to actually move to Loom and understand what Loom is offering. And we're not only looking at syntax and the like, but most of all we're looking what kind of problem do coroutines solve. And we go step by step, starting out with an example that really has nothing to do with coroutines. It kind of helps you to make yourself familiar with it because I will use it throughout the presentation, this exact sample in various variations. So what we do here is quite a simple thing. We eventually save a user in a database, and before that we fetch a random avatar, we verify an email, which are all remote network calls. And also, of course, the save action in database will be a remote call. So far, so good. You might think, okay, what's the big deal about that? And like this lazy guy thinking, yeah, why should I ever learn something new? Or something else, because it kind of works. It depicts really the intent of what I want to express. There's no additional abstraction involved, so we're fine to go. The problem arises when you set load on a system like that. In order to understand what's really happening, let's quickly go through this kind of architecture. This is a typical architecture with a Tomcat Jetty container where you have normally a thread pool with about 200 to 300 threads. Whenever a request comes in, a thread is taken from the pool to handle the request. Whenever the thread hits an I/O boundary, the thread blocks, so it doesn't do something else. Once the reply is received, again it does a network call, it blocks. And that's how these things work. And then the request eventually has been processed. So what happens if, for instance, this resource becomes slow? So this remote web service, all of a sudden, because of various reasons, doesn't reply in a timely manner. Then it can happen quite quickly, as we also heard in other presentations, that your thread pool gets exhausted. And when your thread pool gets exhausted, what happens then is that you cannot take on your requests, leading to very dissatisfied users leaving your site, go to your competition, which you really don't want. Besides that, we also can not really leverage parallelism in this programming paradigm, which could also give us some additional speed in case your use case is suitable for parallelism. Okay, so far so good. This problem has kind of been realized quite some time ago, about 10 years, I guess, by now, where they introduced reactive programming to actually solve this problem. So the code that would be rewritten using a reactive toolkit, in this case, Webflux, you might know from Spring, would look like that. So let's look at how this model works. So instead of having a thread pool with 200 threads, we now have a thread pool with only about 1 thread per core. So if you have a quad-core machine, you got 4 threads. So the question is, how can this system be so much faster and better than the example where we had 200 threads? So we get less threads and more speed. How come? Quite simple. So whenever you get a request, a thread is taken from the pool. But when the thread hits an I/O boundary, it doesn't block, it doesn't wait. It just offloads the payload to the network layer, and continues doing something else. So these 4 threads are continuously spinning, spinning, spinning. Whenever you get a reply, callback, then another thread or the same, doesn't really matter. One of these 4 threads will pick up the work, do something else, hits an I/O boundary when we save it to the database, and the same happens with the reply of the database. The same or another thread will eventually return the response. So if this resource becomes slow, like in the previous case, what is happening? Not much, because the threads do not block, so they can continuously keep on your work. So in that sense, we stay responsive. We maybe cannot serve a decent answer to the user, but we can serve an answer to the user. Maybe it takes a bit longer. We are not unresponsive. Besides that, these kind of programming models also leverage parallelism. So if you have this business case where parallelism is a good match, then we also can use that and speed up our request handling. So we definitely end up with quite some happy users using this model. So far, so good. So as we've seen, this is the code you have to write, and if everything would be fine and dandy, we could stop now, go home, and go to another session. But apparently, there is a caveat, right? So what you have to do in order to achieve what we just seen before is that you have to introduce some abstraction. And not only an abstraction that is in one corner of your code base, it's an abstraction that will dominate your whole code base. And that's logical because these abstractions are libraries, and libraries only come with abstractions. It's no language feature. So this is the kind of buy-in we do when we embrace this kind of model. And this has quite some limiting aspects. So first of all, as you can see, we are all of a sudden dealing with SIP, flat map, do finally. Normally you have a try finally, right? All of a sudden we have a do finally, so why is it needed? Because normal language constructs like if, else, throwing exceptions and so on simply don't work with this model. Which resulted in these reactive toolkits kind of re-implementing these kind of low-level semantics. And the problem is one toolkit is not the other, so if you choose another one, you actually relearn the whole thing. Besides, and I think this is really the worst of all, your business intent is really getting lost. So what is happening in this code, which is relevant for your business, for your boss in that sense, you really have to figure out what's going on. There is some, oh yeah, here I see there is, oh yeah, there is the random avatar, the verify, and then, oh yeah, here to save the user. So you really have to pick out what's relevant for your code. And for maintainability, that's a big issue. And even worse, it is really easy to shoot yourself in the foot with these models because there's so many things you have to be aware of. You can quite easily block things, but then your performance will even degrade, even though you had the goal to actually improve performance. So these are the issues when you use reactive toolkits. And we shouldn't forget one thing, which is quite important to know. Why did we all do that? And I just changed the resolution of my slide to something else and back, but apparently the revert didn't work very well. But what I want to say here, which is very relevant, why did we do all this? For actually 2 reasons. 2 reasons. Maybe a third, but for now 2. Only because we wanted non-blocking I/O and a little bit of parallelism. Because we wanted these 2 things, we sold our soul to this framework, letting us dominate and pollute our whole application framework. So, as a summary, reactive toolkits, they solve the problem with better resources, responsiveness, resilience, and so on, but they come at a very high price. So in other words, accidental complexity. And of course, the question is there a better answer? And yes, there is a better answer. And guess what? These are coroutines. That's actually the pill that should help you answering this problem in a way effective way. So now we're actually at the stage where you can look at coroutines, and you probably see that the benefit they give based on what kind of burden you have if you choose reactive toolkit, which you don't see if you start right away with coroutines, right? Because then you think, okay, you need this contrast, I guess, to understand their value. So the code we have here, as you can see, looks a bit more like the code we had in the beginning, right? The blocking code of the sleeping programmer, which is very evident, which is, again, pure in my eyes, because it depicts what's really relevant. We have normal method signatures, no additional abstraction involved, and this is how you would call this code. So I think this code your boss could read and understand. And that's always a perfect sign that apparently it's code that is maintainable. Besides that, we also can use something like async and await, which allows us to kind of in parallel set out two tasks. Here, random avatar, verify email, concurrently, in parallel. And then continue working once these calls have returned value. So this is actually what coroutines give us. Coroutines allow us to express logic sequentially. And now comes the really cool thing about coroutines, is that the asynchrony is figured out by Kotlin itself. That's quite amazing, because you think now this stuff is blocking. It's not. It's nicely asynchronously executed. So you get some sort of best of both worlds. You write simple signatures, but underneath it behaves as effective as you would have reactive code. Of course, you won't get all this for totally free, right? So there are some things you have to know about, and we will look at them, that you also maybe take home some knowledge about coroutines as an addition as what we heard this morning about coroutines. So we heard probably about, seen these suspend functions. We will look at them in a minute. But first of all, what are coroutines? Was also a bit explained. I think it's good to also see them in contrast with, first of all, processes. On a operating systems, we have processes like the Java process when you start up an application. Don't have many of them. Then you normally have kernel threads. So these are the threads that really get a time slice of the CPU and then execute something on it. And on top, you would have coroutines. And coroutines are lightweight threads, so you can have 2.4 million per gigabyte, whereas in the threading case, you can have about 4,000 per gigabyte memory. So it's quite significant. And a coroutine, in that sense, needs to be executed by a thread. On the GVM, we only have threads, so eventually a thread needs to do the work, but it's not pinned to a thread. So also within the life cycle of a coroutine, several threads can take part. A bit like the reactive example I explained a minute ago. So now let's actually move from threads to coroutine and then kind of figure out what kind of benefits we have. So this is a simple example where we use the thread builder of Kotlin. It's a nice builder that actually does new thread runnable in.start. That's what you get when you call thread. And here I do a kind of bad thing. We do sleep. And as you might know, sleep isn't that great because it blocks. And whenever a thread is blocked, it can do something else. And it's an expensive resource, so we wasted a resource for 1 second. This is what we do here in action. The coroutine example looks more or less like that. First of all, you cannot create coroutine just as you create threads. So there's no new coroutine and then you have a coroutine. You need a builder for that. An example we use here, we use run blocking. That's the builder we use. And as you maybe might guess, there is the word blocking in it, right? And maybe this is kind of hint of telling you, hey, are you aware you're blocking, man? So in that sense, don't use this in production code. These snippets are here because you can run them in the main method, and then it works. But in production codes, don't use them. Really don't. Because I know many people do. That's why I say it. There's always another way around it. But okay, for these snippets, we need to start somewhere, and run blocking kind of bridges the thread world with the coroutine world. And there are better ways to do that, but then it wouldn't run in the main method. So we have this builder. From this builder, we actually now launch a coroutine. And launch is really the same thing like a thread. It's some sort of spins up an asynchronous process. This is what's happening here. And then we encounter actually the first beautiful thing about coroutines, which is delay. And delay doesn't block, but delay suspends and resumes. Which means that when delay is called, the coroutine handling this code is kind of parked. And then after 1 second, something is scheduled. After the second has passed, it will resume and continues working. So, what is the difference between these two snippets? What we do here is we create 1 million threads and we create 1 million coroutines. And if you paid close attention, if the lunch tip hasn't been too heavy on you, I think you can imagine what happens, but I really want to show you because I think it's good to see. So here we have the example with the many threads. We create 1 million threads. Let's run it. ready to roll, and boom, we get out of memory. That's not very surprising because I have 2 GB of memory, 4,000 threads fit in 1 GB of memory, so after 8,000 threads, this whole thing blows to pieces. Then let's look at the coroutine example, that's this one. And I made it a bit more fancy with nice counters and so on, that we see what is more or less going on. So 1 million has been created quite quickly, and after 3 seconds, so then they wait all 2 seconds, and after 3 seconds this whole thing has been processed. Nothing has blown, as if just nothing has happened. It processed a million asynchronous, it spun a million asynchronous processes that did what they did. So in other words, this blows quite quickly, and this just continues spinning. Let's take a closer look at suspend functions, because I think it helps to understand how this whole thing is working. Whenever you mark a method with suspend, what you actually do is you give this method a capability to be suspended and resumed at a later time. This is actually the capability you gain. When you look what is compiled, is the code you see here. Actually, an additional parameter is compiled in, which is called a continuation. And continuation is a fancy word for actually a very simple callback interface. And callbacks actually have always the same interface. They have a value for the good case and a value for the bad case. So the T and an exception. So under the hood, it's just plain old callbacks, but abstracted away in such a way that you don't feel it. And what Kotlin does actually in the code it eventually compiles is that whenever such a coroutine is suspended and then resumed, it has some state machine where it knows, okay, I've been left off here, this is where I've continued, this is the state that it belongs to it, and then I continue. So the problem we had with the reactive toolkits with all these map, flatback, and so on is just solved on a language level. So let's look a bit closer what kind of ingredients we get, because then for Loom this kind of helps. Because there are some really corner cases involved with it. So we have actually, these are the builder methods, and they have 2 parameters. The first one is the coroutine context. As you see, you get a default context. That's why I didn't define it in the examples I saw. I said run blocking, and then it was good. But yeah, the context can have a variety of things. And one thing is very important to know is that you need a dispatcher. And eventually, a coroutine needs to be run with a thread. So you need some sort of thread pool. And by default, you get the default thread pool, which has as many threads as you have cores. And you can also have other things like state that is bound to the coroutine, exception handler, and so on. So the second one is actually the coroutine scope we look at, and this gives us something tremendously cool and powerful, which is structured concurrency. But first look at what structured concurrency not. And this we see in the thread example. So in the thread example, if we want to join third an asynchronous operation, we need to do this manually. This is what you do here with calling join. The problem with join is that, guess what? It blocks again. So in these 5 lines of code, we again wasted a lot of resources. So the first thread that waits for a second, but the second now also waits for 1 second because the first one hasn't finished. So we actually introduced 2 times a blocking operation. In coroutines, this is really solved tremendously beautiful, and I think this method signature above is probably the most fancy you've seen today, maybe. At least for me, it was when I saw it for the first time, thinking, okay, what is this? So this is this function literal retriever, lambda retriever, as we've seen in the type-safe builder example, but then it's a kind of suspend one that needs to be in this suspend universe. And this coroutine scope is a tremendously cool object because it actually manages the life cycle of a coroutine and also coordinates the completion of coroutines that could be infinitely nested. This is actually what the scope gives us. And with the scope, we can do structured concurrency. So when I say run blocking, I get this actually refers to the scope. This is what this function literal with retriever give you. This would then be some sort of root scope, and coroutine scope I actually call on the root scope. That's where I create this coroutine scope. And this coroutine scope I would introduce if I want to say that this block needs to terminate first, no matter how many asynchronous processes I spawn within this block. But I want this code to finish first before I proceed. So this is actually how you get clear defined structured behavior with asynchronous processes. So this is what's happening. We call coroutine scope, which has a new scope, which is a parent. Then on the parent scope we call launch. Here we really spin up the new process, which is a child scope. And as said, scopes, parent scopes coordinate the completion of child scopes, and this is actually how we then get what we want. First, started is printed, then after 1 second, after 1 second is printed, and eventually done is printed. And nicely, in a beautifully structured way, and important most of all, it's not blocking. Okay, so now you might think, that's wonderful, this coroutine, it's pure, it's good, it takes away quite some nasty stuff for me, but the world out there isn't as beautiful as this coroutine. So if I have this reactive framework of this future, completable future, whatever, how do these two things interact? Probably would be a nightmare if you had some different asynchronous primitives in your application, a bit coroutine, a bit futures, and somehow it works or doesn't work. Okay? And also about this, they thought very carefully. So what we have is a very simple means to kind of lift existing reactive code into coroutines. Example we have here. So this is the example we would use for this random avatar method, where we use the web client. Don't know if somebody's used it. That's the asynchronous, powerful tool you have in Spring Boot Reactor to make asynchronous network calls, which returns a mono. And then again, we go with the mono and the mono all the way. In order to turn this into a reasonable method signature, the only thing you have to do is you have to make this method suspend. And second, use one of the many provided extension methods that converts this mono into a suspended method. That's all you have to do. And then, literally, the mono abstraction has disappeared. So this code still lives on the Reactor abstraction, because there's nothing wrong with the Reactor abstraction, right? It performs beautifully. It's just the programming model that is so horrible. But lifting it into coroutines, we get the best of both worlds. We get a manageable programming model, which also performs in a very effective manner. And this would be, for instance, the controller. This really all works in Spring Boot. Beneath it's all Reactor, but on top it's just like normal code you write. And the beautiful thing on top of that is that the general language constructs like if, else, throw an exception, try, catch, no matter whether synchronous or asynchronous, just works out of the box. So yeah, I think it's really beautiful. We use this stuff also in production, and it also really works great. It's easy to maintain. Also for less experienced programmers, it's just really the perfect way to go. What we haven't talked about is another abstraction you cannot solve with coroutines. This is the one where you have a sequence of asynchronously computed values, reactive streams. There you need an abstraction. Kotlin offers this one, which is flow, comparable to Flux in Reactor, flowable in RxJava. And the nice thing about this one is that it's part of the standard library. So once you learn flow, you learn it once and you can use it no matter which reactive toolkit you use. And also flow can be nicely adapted to all these different reactive frameworks. So to recap coroutines, because then I think it's time to move on to the meat of the presentation, which is Loom. We have lightweight threads. We have the way to write synchronous logic, which is executed asynchronously. We have structured concurrency, allowing us to orchestrate many asynchronous processes in a very understandable and maintainable way. We have Interop with these reactive frameworks. And is it non-intrusive? Okay, you probably might guess it. It is intrusive. Because we have the suspend, we need a coroutine scope in order to make all things work. So it's, in that sense, intrusive that when you start out with a blocking method and then you call a suspend method, it's not going to work because a normal method doesn't have this context. Yes? Definitely, definitely. That's correct. So, calling from a blocking context a suspend method, this is what people do. They use run blocking. This is not what you should do, right? Because then you still block thread. This is not what we want. So this is not going to work. What works is that you start out with a coroutine scope and then have other suspend functions calling suspend functions. That works. You can call a blocking method from suspend function, but not from blocking suspend function. In that sense, yes, it is intrusive. Okay. So, but as a bottom line, coroutines really offer you hassle-free concurrency, really. And I've experienced it myself. It's a tremendous difference in comparison to the reactive toolkits. Of course, Java wants that too. Now I think my whole animation is gone, doesn't matter, and this comes in the form of Project Loom. What is Project Loom? This we'll look at in a minute. And the good thing is that now we have actually our checklist to see what needs to be there in this Loom to kind of make it comparable with coroutines. Project Loom was started around 2018. 2017, Kotlin really got traction. I don't know whether Kotlin also was some kind of incubator to make Loom more active. Its motivation is to create high throughput, lightweight concurrency for the JVM. Its status is still experimental after 3 years, and it will, I guess, stay still so. The examples I'll show you today are the ones that are part of GDK 17. It's already part of GDK 18 now. Probably won't be finally released in 18, it will 19 or 20. But 80 doesn't work in IntelliJ, so, and already changed again some features. So in that sense, it has no official release date. I asked JetBrains, hey guys, what happens when Blooms comes? What is the route? They say, no comment, because there is no official release date, we don't comment. So the certain things I show you a bit interpretation on my side, but I think it's good to envision what happens and how this could impact us, at least when we have to make decision now, knowing that this will eventually arrive. So it's work in progress. However, the core design is kind of stabilized. This is what I see in the last year, maybe. Okay, how does it work? Loom. This is the operating system. You have CPUs, you have kernel threads. We've seen that these kernel threads are expensive. They cost about 4,000 or 1 gigabyte for 4,000. And the Java model currently, actually since the beginning, more or less, binds its threads more or less directly to a kernel thread. It's not more or less, it really binds a thread directly to a kernel thread. In Loom, they introduce a new concept called virtual threads. First they called them green threads, fibers, all these terms have come along. Now it's virtual threads. Maybe tomorrow it's something else, but I think they will stick to virtual threads. What a virtual thread? It's actually exactly the same like coroutines, conceptually. So you have these lightweight threads, you can spin up as many as you want, so millions at least per gigabyte. And yeah, in the end, a kernel thread needs to execute them, right? And they had this construct of carrier threads, as they call them, and these are threads you cannot access. This is kind of hidden for you. You just deal with virtual threads, and that they're executed by a real thread, that's not your concern. Besides that, we still have normal threads, because sometimes you need to have CPU-bound work, where you just want to be as close as possible to a kernel thread, then you would use a kernel thread. But for all these I/O stuff, these virtual threads are really great. So how do they look like? And this is Kotlin code. So all the Kotlin code that was possible with virtual thread, I show you, and some code is not possible. And I hope you won't be too shocked. You see this Java code. So this is the thread example, which prints thread. And this is the virtual thread example, which prints virtual thread. So, can you see the difference? Hey, there is no difference, because virtual thread literally extends from thread, but it gives thread different semantics. Okay. That's what I thought first time. So let's look at the difference. We had the coroutine example on top. Below we have the virtual thread example. Let's see if this performs a bit better compared to the normal thread example. So this is the start virtual thread. Let's hit the button. Make it a bit more readable. And see, 1 million is created quite quickly, but then, takes quite some time to process them. So things, apparently gets the job done. It took about 12 seconds, whereas the coroutine example took 3 seconds. So I think Loom still has some work to do there. But it works, kind of, right? We can now spin many threads. So lightweight threads we can tick. The thing that is really cool about Loom is that they did something very ingenious. They rewrote actually the blocking I/O clause. So whenever a virtual thread hits a blocking I/O operation, they kind of automatically switch to a new I/O operation, which works asynchronously. So they do exactly the same like with coroutines. They suspend the call, and then they resume once your network has replied. And this they did actually for all kind of blocking constructs within the GVM. So also some certain I/O class that are blocking, Java with concurrency, the locks, for instance. So now, all these old-fashioned, for instance, REST template, all these blocking constructs we used years ago, all of a sudden perform as well as these reactive beasts like web clients, which actually makes them obsolete. And you get again these pure signatures, so you get back a real image, but beneath it performs as well as the reactive counterpart. I think so this is really cool. So how does it work? Actually same like the reactive example, except that you don't have a thread pool at all, because you can spin as many virtual threads as you want. And the behavior is the same as we said. Virtual thread hits I/O, then suspends. Once the reply comes back, another carrier thread will pick the virtual thread and continuous processing, and so on and so on. And the result is exactly the same in terms of resilience like the reactive stack. So if something becomes slow, we still can take on requests because we can have so many of these virtual threads. So also parallelism we can leverage. Everybody happy peppy. Yeah. So the point is that you think it's blocking, but in fact it's not. It's an I/O. Okay, let's look at how they implemented structured concurrency. I have some minutes left. So this is the sample we saw before. In Kotlin, this is how it looks like in Java. Java has a problem because Loom doesn't introduce new language features. Loom gives new semantics to an existing construct called thread. So in order to make something structured, they needed an existing construct to put it in. So they were looking, where could we put it in? Okay, hey, we have this try with resource block. Maybe there we can put it in. That's what they did. So they kind of re-abused try with resource block to make this section execute before the next. So no matter how many asynchronous processes spawn with this executor service, this is how they implemented structured concurrency. So coroutine scope is same like try with resources. When you have async await, we've seen in Kotlin, you have this async, then you get back a deferred as it's called, you can call await in it, but in Kotlin it doesn't block. In Java, they haven't introduced a new construct. So all of a sudden these nasty 1.7 futures, which had this blocking.get method, all of a sudden good again to call. Because yeah, you think it blocks, but it doesn't, because it's a virtual thread. Okay, so actually all these reactive constructs that have a blocking method, the ones you shouldn't have been called before, in mono it's block, in coroutine, in completed future it's join, in future it's get, is all of a sudden good again to call as long as you are in a virtual thread context. Yeah, let's talk about exception propagation. In Kotlin this just works as you expect. In the virtual thread example, it works when you do a get, then you would get back the exception. However, if an asynchronous process throws an exception without returning something, your exception just vanishes in limbo. Whereas in the coroutine case, you also could do a try-catch around an asynchronous computation. So there it's not really perfectly implemented. So you get some sort of structured concurrency, but not to the full 100%. So kind of. How about interrupt? So there's not really interrupt, right? Because Java still needs these reactive frameworks when you do, for instance, things like async and await. It just gives actually a new dimension to existing reactive frameworks. So all the blocking methods are kind of okay to call again. This is actually what it does. And yeah, I really kind of feel sorry for the poor souls who are confronted with that, because this can get very, very confusing. So look at this example. One is good and one is bad. I know it's a bit a lot of code just to get it in your face, but I help you a little bit. So what you do is we create 3 calls with the REST template, blocking network calls. The first example is fine, the second is not. Why? In the first example, we use this virtual thread. In the second example, we use a normal thread, new fixed thread pool, so an old-fashioned kernel-bound thread. And when we call in the second example .get, we block a thread again. How we explain to someone who hasn't really worked with thread that this is working this way? Good luck. So same syntax, different semantics. So we've seen lightweight thread, that's fine. In terms of this synchronous expression, Loom, I think, really is better than coroutines. Non-intrusiveness, Loom is definitely better. Structured concurrency is better again in coroutines. And in terms of interop, coroutines is way better because Java doesn't really have interop. So this is not the conclusion of my talk, because what will eventually happen is this. It's Loom with Kotlin, right? And the question is, how do we end up? And I think this is going to be really a wonderful future. And why is that? Because we can assume that coroutines probably need a makeover, right? So as they work now, they probably won't function. So maybe suspend keyword might disappear, I'm guessing here, but it doesn't make sense when a virtual thread to have this kind of intrusive context. Not necessary anymore. But we most probably get these beautiful builders again, which allow us to create these virtual threads, to have the scope nicely working as you would expect. So we might get beautiful builders that make this virtual thread as manageable as with coroutines, with the benefit that they are non-intrusive, as long as it's virtual thread. I think that would be really great. Flow will stay because we need such a construct. Maybe also some changes there, because Flow has also some suspend methods. They probably call differently. So all in all, I think the impact for Kotlin, for you as a user, I think for the design team, it will be a big impact to make this all work. But for us as a user, the impact, I think, is not very big, very large. For Java with Loom, I think for 70 to 90% of application, there is also an impact, as long as you don't interact with threads directly or use a reactive toolkit. So if you just use these normal Spring Boot applications that are all blocking today, you kind of get a boost automatically. However, if you're using threads or reactive toolkit, then we get this confusion we saw before. So depending on whether you're in a virtual thread context or a normal thread, you really have to behave totally different. How you make this understand, developers already have a hard time to understand all these reactive constructs. I think it's really going to be an issue. And so at least the asynchronous processing of these reactive toolkits just you can throw away. So if you're sold your soul to this reactor, then yeah, I think your soul is kind of lost. So to round up, we had some insights today how this Loom works. Think, how does it impact the decisions we make today? The decision tree I use is as follows. So you really have to ask yourself, do I need this high throughput resiliency like in React's applications? Do I really need it? Or is it just enough if I can spin up another container and it will also perform good enough? And if you don't need it, then I would say, just stick to your blocking model. It's fine, because eventually Loom arrives, you get the boost yourself. If you have a business case that you need this robust, resilient, and so on model, then I would say, choose for coroutines, not for the reactive stack, because you get, first of all, a way more manageable programming model. Coroutines are almost the same like normal code, except you have a bit suspend functions. And when Loom arrives, you probably only have to reduce or remove the suspend keyword. Maybe there's even a converter in IntelliJ Web which says, okay, convert to Loom. I can imagine they're going to build this. And then your application just perfectly works in harmony with virtual threads. So this would be my advice. So to round up, if you're a developer like him sleeping, I think it's a good time just to continue on sleeping and wake up over maybe 2 or 3 years and the world has become a better place. Okay, thank you.
Nice job, man. Well done. So for our physical audience, we're going to have a choice, actually. You can either go have a break, and we'll be back at 2:45, or next door, we're going to have a talk on how Kotlin makes Lombok obsolete. So your decision. Seats are limited there, so first come, first serve. And for our audience back home, we'll be back at 2:45. Thanks, guys. See you in a bit.